So, good morning, everyone. Welcome to the third day of MACH2021. And the first speaker of the morning is Maurelli from the University of Milan, who will talk us about randomness in marble sulphation. So,
Okay, so thank you for the presentation. Thank you, Ceseri and all the organizer for the opportunity of being here and giving this talk. So this talk will be about how to insert and why to insert randomness in the process of sulphation in marble and similar material. This is a joint talk with Daniela, Morale, and Stefania Volini, who are not here, is also jointly prepared. And this is a part of our Shipult project, which is a project that we have in Milan about joint mathematical and chemical analysis of the degradation, in particular of outdoor monuments, in particular about sulphation catalysis. Okay, so as I was saying, so we would like to describe put some randomness in the marble sulphation. Why should you do that? Well, the idea is that, as we will see, some quantities exhibit large heterogeneities and uncertainties, and for this reason, the description of these quantities through just as deterministic fixed quantities is may not be that so appropriate, and rather the description through probabilistic and statistical tools is probably more. Okay. The question is, what are then where should we put randomness, right? So which quantities should we put randomness, and then also what is the effect of these uncertainties, these heterogeneity in the sulphation process, right? So I should say, since we started also a few months, we do not have yet answers, but we rather have questions. So we, in particular, there are some things that maybe you know and we do not know, and we would be happy if you tell us some suggestions. Okay, so let's start with the sulphation process. I was lucky because Roberto Natalini already explained this model in the first lecture. So this is the transformation of calcium carbonate into gypsum under the chemical aggression of sulfur dioxide. Okay, so you may not care much about it. Even if you don't like much equation, don't worry. Here we are just saying that the sulfur dioxide diffuses inside the pores and reacts with the calcium carbonate to produce gypsum. Okay. In particular, I want to so here the X is the local the porous concentration of sulfur dioxide. C is the local concentration of calcite, and phi is the porosity. Okay. All right. Now, okay, as I told you, there is a lot of heterogeneity. In particular, you can see this from these pictures that you can also guess that there is the microstructure of the materials. There is heterogeneity. So here you see a picture of marble. Okay, you see here these are. For example, the grains of the calcite and the interface of the grains where the sulfur dioxide may flow and the air may flow are these lines, right? And you see that there is not a clear structure, there is not a clear order, so it could make sense to describe these random objects. Another picture is taken from another picture taken from the paper of Valeria Comet and Paolo Fermo and other people, authors, shows picture of both calcium carbonate here in blue and gypsum in this kind of yellow. Okay, here you see an enlargement of this piece here. This picture gives an enlargement of the square in picture C, showing again that there is quite some heterogeneity. For example, in this region here, I hope you can see the pointer. You have not so much porosity here. You have instead. Now, the point is not sometimes it's not easy to measure these heterogeneous quantities. Okay. And sometimes one takes just macro model, not macro model, and so sometimes this brings to not considering this heterogeneity. We have seen in particular yesterday talk of Panicopoulos, very nice, derived from micro to macro, this model. However, it could be that this heterogeneity, this uncertainty still remains even at the micro level. And taking, so ruling out heterogeneity by taking average could bring to not the right result. I will try to show you a simple example about that later on, about this, very simple. Anyway, so our program is, first of all, to understand where it makes sense to consider heterogeneity and then randomness within the model. This will be most of our talk, because, again, we started from a few months. And then we would like also to use the model within, so with such random data or heterogeneity to predict the possible effect, to understand where, if and where random plays. So let's start with the first proposal of randomness. Okay, so the stochastic porosity. So we will like, so the first idea is to put stochasticity and randomness in porosity. The model is always the same, right? And I just recall that porosity phi is the empty volume per unit volume for infinitesimal volume. As it was told, it's not really, in some sense, practically may not be well-defined quantities, but mathematically one can think of that for infinitesimal is quantity for infinitesimal unit. Again, I was lucky because Roberto Natalini already showed this, how to express the porosity under certain assumption as a linear function of the calcite concentration, right? But here you see that we need these coefficients. You don't care much about the form of these coefficients, but what you see is that there are some constant quantities, which are the mean molecular volume of calcite and gypsum. And then you have the psi 0 and G0, which are the initial concentration of calcite and gypsum. So this appears in the formula for phi, right? And okay, I think originally these are in principle are not assumed to be constant in space, psi 0 and G0. But often later on they are actually taken to assume to be statistic coefficients in B are assumed to be constant, and therefore one kind of assumes that these quantities are homogeneous, are constant in space. So our first idea is well, maybe given the picture that we have seen, given the heterogeneity that we may expect, one could actually remove this assumption, and so one could consider coefficients, the coefficient A within the formula that we've seen before, as a random field, right? So it's a field which is randomly distributed. At the physical level, what does this mean? As I told you before, this means that, let's see the second bullet. If you imagine that you have your marble at the initial time when there is no gypsum, right? So you have just calcite. So basically the phi depends only on the initial density of calcite. And so the initial porosity, just the initial porosity of calcite, we are just saying that the calcite is a random porosity. So the porosity of calcite is not homogeneous, it's not constant in time, it's not constant in space, sorry, but is actually randomness. And then here comes my first question for you that we did not manage to find in the literature, but maybe you know some answer to that. If it makes sense to consider calcite which has a random porosity, what are the statistics of this porosity, right? So, for example, what is the correlation function or things like that? We just a more mathematical results, more mathematical remark. We have found some other papers, for example, here about sand, which gives some statistics for the random porosity. This is actually no smooth, which of course causes some challenges for us. Right, so when it comes to closeness, maybe also numerical explanations. Okay, so the first proposal is to put phi, which is random distribution. Again, about random porosity, we may go further. So far we did not think. So when I told about random porosity, I did not think of modifying the model, but rather put as a phi a random object, right? A random distributed porosity. We could actually go a bit further and say, okay, we definitely observed. I've just put here two papers which report that, but I think it is well known that the porosity decreases due also to formation of gypsum crystals. Okay, and so. The idea is whether, again, maybe you can recall the pictures. Maybe I did not mention. Sorry for that. Let me go back to this picture here. You see here these are gypsum crystals, and you see again there is not a clear structure. But you see the structures actually, but they are not distributed in a very orderly way. Right? So it could make sense again to describe this by to describe the process of crystallization by stochastic means. Right? I'm not an expert about that, and I should say I was happy to see at least a couple of tutorial talks about that crystallization in this workshop. So for what we know, I see at least two ways to reproduce this. So first of all, one may try it again to give a macroscopic description of the crystal growth, right? So this means that the porosity phi changes over time. So here we have taken this by a paper of Chadam, and the porosity phi, ignoring radiation, one would see the change over time of the porosity phi depending on the coefficient G, which gives the rate of the volume change of the crystal. So it describes the growth of the crystal, right? So within this model, for example, we can considering the randomness maybe to be translated to consider a random rate of growth. Right? But anyway, we are not expert of that, and the input from you would be well. Then there is also
just a question.
Yes.
For the previous slide. Clearly here you don't need the equation, so you instead of solving the equation for C,
yes,
you are replacing for the equation of G.
No, sorry, this is sorry, good point. There are other equations. I just not put here for reason of space, but you are saying this is not somehow needed. So I could apply for.
I mean, if you know, I mean, you can. Okay, it depends on the structure of the project. If it is, I mean, inversely, with respect to C, you don't need another equation.
Okay, so you are saying I can forget about the C then.
I mean, in the previous formulation, even if A depends on X, so it's clearly monotone in C, so you can inverse it from C,
yes,
from the equation. So I mean, say.
Okay. So you are saying I could just consider phi only, and even the reaction here. Okay, maybe even you can forget about C.
No, you can forget that. Yeah, well, C.
Okay.
You can replace it in word. I mean, if you introduce some statistics in the formulation of policy, it will be changed because it's not no more a function.
Okay, I see.
Yeah, but if the growth rate depends on C on the pixel, so there is the connection. So it may be needed. It depends on how is the path.
Sorry. I'm sorry because there was a question. So Roberto Natalini was suggesting that in this equation I could basically forget about the C. As far as I understood, because the relation between phi and C is 1:1.
At least since it is until it is deterministic.
Okay. Yes. Right. So here I could find a way and.
Even the stochastic should get into anyway.
Yes. Well, I invert the relation. Okay, anyway, sorry. Let me just maybe. Can I just maybe go further? And then we can.
Maybe we can postpone the question, otherwise,
Okay.
online.
Okay, so okay, so let me go to the final things about random porosity. We could actually even try to describe this at microscopical level, right? So give a microscopic description of this crystal growth as variation. And in this case, the keyword would be Poisson processes and random tessellations, right? So here I have the picture of random tessellation. So not taken here from marble sulphation or just other model. So maybe one could then try to do an homogenization and as in yesterday talk. Okay, so this closes our first proposal about random porosity. Let me go about the second proposal, which is actually very much related, which is about stochastic permeability. Again, I'm lucky because this model was already presented by Roberto Natalini. So the idea is to introduce the movement of the air within the material, and this brings to produce pressure and in particular permeability. Right? We don't care exactly here about the form of this equation. My main point here is that at least, I mean, there should be, so the permeability and porosity are not the same. I was also talking yesterday with Roberto Natalini, but so the permeability describes the capability of the fluid to run into the material, but there should be some relation. There might be some relation because, of course, the larger, the more connected the pores are, then so the larger the porosity is, I would expect also the larger the permeability is. In this paper, which we got the relation between porosity and permeability, this is the intrinsic permeability. So I'm not sure it's exactly the same object that we had before. But at least this shows, this is not important to match this relation here, but the main point is that if you expect to have random porosity, then I guess you should expect also to have random permeability. Okay, so there is something about the mathematical literature about that. Maybe for time reason, because I'm already out of time. I will not talk too much about that. This is a linear model, very much simpler than the model that I want to describe. But just to say that there has been something in the mathematical literature, where this K is a very high oscillating field. This permeability is a very high oscillating field. This in particular the exponential of the white noise, which is decorrelated field, random field decorrelated space. There is again some mathematical challenges because in order even to define this object and solve this equation here. I guess, however, this is not the most realistic, again, statistics for K. This, by the way, this is taken by a book of by Holden and other people about SPs, and also our former students, Andrea studied this, and also the previous model within his master thesis last time. So anyway, the question again is which statistics should we take for K? And then also, if case very rough, then the coupling with the other equation not be that much easy. Coming back to the introduction, the stochastic permeability also gives me the opportunity to explain the idea that sometimes if you average out, this is not. This is a very simple example, so it's too simple. But let me say, so this is not exactly the linear pressure equation that you saw before, but it's another model. It's the model for moving. Is the model for the moving boundary problem for pressure in a wet region. So you some. In this case, some water in its points. The water diffuse in a certain region, which is the wet region. Here we have a linear pressure equation, and then you have the equation for so the region where the water flows, right? So you see that if you have a constant porosity, then what you expect is just that the water expands through increasing bolts within the space. So very simple picture. But this is not what you see in experiments where you have, this was an experiment where you have a non-constant permeability. And you see that the picture is completely different here. This is quite statistically unexpected, but just to say that if you say, okay, let's just take average permeability, does not give the right result in this context. Okay, let me now finally go to the last proposal, the third and last proposal about stochasticity, which is not really about heterogeneous heterogeneity inside the material, but rather is about external condition, and specifically it's about external sulfur dioxide concentration. So this again, I have to expand the model. Again, this was recalled by Roberto Natalini stock. So the idea is to consider the surface of our monuments, which is very much rough. So the idea is that the sulfur dioxide flows in or out the monuments. Okay, according also to the rugosity of the surface, and the rugosity also evolves according to a certain equation, which here are not called that way, quite difficult to inform. Okay, so this paper, okay. So in this way, we can introduce the external SO2 concentration and also the rugosity. So the effect of rugosity was already explained, but let me just briefly recall. The high rugosity value offer a wider surface for the SO2 to diffuse inside the material. Now, actually, at this point, there was already randomness introduced in that paper. So the idea is that the surface of a monument can be very rough. So imagine on stage, of course, there is a lot of change of the surface. So it makes sense to consider a random initial velocity, right? In particular, in the paper of Bonetti, Cavallero, Natalini, and the other authors, this random initial velocity is considered with a so-called Bible shape, let me say, roughly speaking, is the generalization of the ocean shape. Here are some simulations taken from that paper, I think with the parabolic moon, remember correctly. So this is the initial velocity, okay? And you see that how it evolves in time. So this is after 100 iterations. And you see that the profile remains more or less the same, but with increasing oscillation, slightly increasing oscillation. I'm not sure you can see this too much here, but there is a slight increase of the oscillation. Now, as I told before, our idea, however, is to introduce stochasticity in another, also in another object, which is the external SO2 concentration. What is the effect of this external SO2 concentration? As you may imagine, whenever you have higher value of external SO2, then this means that you have a higher flux within the molecules, right? This is quite expected. However, I think for simplicity, in the paper of Bonetti and other authors, S bar was considered to be constant in time. Now, you can imagine this is one could improve this assumption considering S bar a more realistic way to consider S bar to be time dependent. And indeed, here is another picture taken from another paper of Natalini and other authors. This is the picture. These are data of SO2 concentration in 2006 at Milan, which is even close by here, which shows that the S bar is not a whole constant. In particular, you can see that in most of the days, this is actually below 1, or even sometimes often below 0.5, but there are some peaks. Not too much, I would say, about 10 peaks are higher than 1. Right? Actually, in this paper, this data are put into the model considered here, but not in the model of sulfation that I presented before. Anyway, so it makes sense for us to describe the external concentration S bar as a stochastic process. And for those of you who are a bit more acquainted with the stochastic processes, let me say this process could be a Levy process with the Gaussian component and then a jump. So this is the model that we may try to study, where our external concentration S bar is again a stochastic process, Levy process before. I was discussing yesterday with Roberto Natalini. Maybe this is a too difficult model to start. We may start with rather consider the one-dimensional case. Okay, anyway, so what are the questions? Okay, first of all, the data for S bar was not easy as far as I remember to get the data for S bar, so maybe then we would like to do some simulation about the system. I think the most important question is the following. Well, what is the effect of this random S bar? The S bar I recall is the external concentration, but what was more important, for example, you see these high peaks, and then the question is, what is the contribution of these high peaks in the sulfation process, right? So in particular, do they contribute? For example, is the dust sulfation happens as a consequence of most of these high peaks or not? So as again was the question suggested by Natalie. Okay, so to sum up, I hope I'm not having time. So here is I've given 3 proposals of randomness. Random can play a role. I have some questions for you especially about statistics for porosity and permeability and model for crystal growths. And finally, is to understand the effect of randomness. And that's all. And thank you for your attention.
Thank you. Are there questions, remarks about? Oh, please. You should come here, probably.
Thanks a lot for the cool talk. Can I sit here close to you? Yes. So you covered basically everything, right? Either stochastic homogenization or stochastic homogenization, and believing some PDEs and plugging randomness in various places. Or third thing, which could be the most global thing, is what you just showed. Can you go to that slide with red equation? Because that is quite intriguing. Hold on. So you have here 2 processes, right? Yes. Can you please comment on that?
Yes.
These 2 guys.
So the first one is a fractional Brownian motion, the WH.
Fractional?
Yeah, I mean, the idea is that it may not be, we don't know if the statistics here.
The previous one.
Exactly. So it's, I mean, okay, so this data, we don't know whether it makes sense more to consider just Brownian motions, so H equal to 1/2 or fractional. Okay. And the second one, let's say, is jump process, for example, or some process.
Question.
Yeah.
How does this live on the boundary? How can you make it sure that it lives on the boundary?
Right. So I mean,
So
let's
it's
say
a process like which pushes you.
no. Okay. Let's. I mean, the boundary here is a space boundary, right? Right. So let's imagine we have a one-dimensional field, which is easier. Otherwise, I would have a next dependence, which I don't have here at the moment. Okay. So and then there is this is just. I mean this is just depends on time.
So you have no axis here.
Exactly.
So it's just, okay. So then you don't need. And then how do you? What is this on physical property?
This is a drift. So far, we did not have. I mean, this is taken for general.
In the weather.
Could be.
Okay. Also, thanks.
Any other question, please?
My question is not a mathematical question, obviously. I wonder the main topic, the main goal is just finding a quite
online.
Is to describe in a very general way or just modeling some real situation, because from a certain point of view it would be quite useful to use this network of exposure sites where you can simplify the study, just not looking at the situation of very old systems, but just starting from the beginning and looking at the beginning of the mechanism, just taking the parameters. This would help or is not the problem, it's just modeling. I mean, some of these quantities in the model could be replaced in an effective way with some function, numerical function fitted from properly derived experimental data. I hope that I put the question.
Okay.
You know, we have different experience, and it's not always easy.
So thanks. I mean, it would be nice to discuss about, because I'm not understood all of the question, but it's probably my fault.
I can synthesize. Maybe it's okay. Some of the function that you have to guess with some models would be more easier for you to understand the main goal with numerical fitting on experimental data or not, because I was not able, you know, I'm not a mathematician, so the dates is
So that's around how do you verify the model is correct? What kind of
Okay. I mean, so I mean, I think at least concerning okay, let me say one of the motivation is for modeling purposes in that sense, right? So for generality, we want to understand in some sense, at least theoretically, if you put some non-random permeability or whatsoever, it has a different effect. So in that sense, we are at first at least we are not thinking of fitting, but of course this would be another. I mean, fitting is another thing that could be nice to do. I mean, concerning, for example, the model. Sorry, this model. Once we have the data, there are fitting. This is quite standard. There are fitting procedures that we can do and try to fit the data. So in that sense, this is possible. For the porosity, this is a more challenge, at least in the sense that, as far as I understand, it is not easy to. And this is in some sense my question for the audience, perhaps, how to get the statistics for the porosity. So this is not easy. Maybe there is another thing. Since you talked about effective, one could try to do some homogenization analysis, so try to see at large scale. I just want to replace this stochastic data with one deterministic data. The question is, how should the stochastic data, microdata, and deterministic macrodata should talk to one each other?
Thank you so much.
Thank you. And if there are no other questions, thank you. second speaker, Semplice, from the University of Insubria, and still on marble sulfation, but with another point of view. The talk is towards numerical simulation of marble sulfation on superior geometries.
Thank you. Maybe I'll try with the microphone. Let's see. No. Okay. Now you can hear me, I guess. I hope. So thanks for the introduction, and also many thanks to the organizers, because in these days organizing a conference in presence is a kind of bravery, so it's really appreciated. And many thanks for inviting me and giving me the possibility of giving this talk. Talking to at least partially to real people here in the group. So before I start, let me just credit my co-authors. First and foremost, Matteo, still officially in Bruce, but soon to be back in Italy at last. And he has provided the level set discretization, which he had developed during his thesis to perform computations in magmatic chambers, and that we are now adapting to these computations for monument conservation. And then Stefano Serracapitano and Maria Rosa, whose contribution will remain actually in the shade today, because they are numerically characterized, and they are the people that can actually make these computational methods that I'm going to talk about efficient, and they can turn a method from running into days or months into numerical simulations that can be performed in something like hours or a day. Okay, but I will not this is not the place to go into the details of really their contribution. But let me mention them here in the beginning, because it's crucial what they do for us. So go forward. No. No. Never mind. Let's go. The old fashioned way. No. So this is the plan of the talk, and let's start. I'm really talking about marble sulfation, but as Natalia explained in the first day, really the equations describing the sulfation of marbles are just an example of many models involving reactive flows in porous media. So even though I will talk about marble sulfation, any kind of process that involves the diffusion of some pollutant inside the pores of a material and a chemical reaction transforming the material there will likely have a very similar mathematical model to this one, and will likely be amenable to numerical simulations with the methods I'm going to talk about today. So these kind of equations have been sort of shown by Mario before as well. They sort of express the rate of change of some variables, and in this particular example, they're going to be S, the concentration of the gas, sulfur dioxide in here, and the some concentration of calcium carbonate. Let me put it marble for simplicity. And the right-hand side of the equation will be typically composed of two different kinds of terms. Some terms will express the rate of change of the S and C variables because of the chemical reactions, and these terms will not involve derivatives in space. And some other terms, like this one, will express the fact that the gas diffuses into the pores. And these are the terms that will contain typically second order space derivatives. And before resorting to numerical simulations, you can make analysis of the system. For example, you can derive results like this fact that the evolution of the thickness of the crust goes to the square root of t, which Roberto talked about. And this is already very important information. But if you think about it, we'll tell you something precisely if you are at a point in the middle of a large flat wall. Because in the middle of a large flat wall, this process is in fact one-dimensional, because there's only one direction of penetration of the gas, which is the perpendicular to the wall. Already, if you are maybe at the corner of a building, then you have two possible directions of penetration of the gas. So it's clear that here in the corner, the quantity of gypsum that will fall will be higher than further away where the surface is when your wall is completely flat. So in these kind of situations, performing numerical simulations on the real geometries can give you quantitative information on how much gypsum is forming here, and for example, how much this corner will get rounded under the action of rain or other sort of effect, taking away the gypsum from the surface. And how do we do this? In some way or another, what we do is that we choose a grid of points inside the object, which is a square in this very simple example. And at this point, we store, compute, and evolve in time this quantity S, and these are the quantity C, which are representative of the amount of gas, the amount of marble that is present around that point, in some or another sense, depending on the specific numerical discretization technique that we're using. Okay, so here I'm really talking about finite differences, but if you know what are finite volumes of finite elements, you recognize that the values that we compute are representative of the real physical variables around the place where the degrees of freedom is placed. And basically, in order to compute the evolution in time of these variables, we have to solve a large number of more or less difficult mathematical problems, like solving large nonlinear systems of equations, and in turn, large linear system of equations. And we have to ask ourselves, is my code efficient? Does it speed up correctly if I run it on a large supercomputer rather than on my laptop? And all these kind of questions that whose answer is crucial to be actually able to perform a simulation in a reasonable amount of time. These kind of questions I'm not going to deal about here because this is not the right audience to discuss this stuff. But please bear in mind that there are a lot of technical details that I'm sweeping under the carpet that needs to be taken care of before we can actually perform a real simulation. What I want to talk about today is the fact that if you are a restorer or a conservation expert, then you're not dealing with objects which are flat surfaces or little square of cubes. You're dealing with objects that have complex shapes. Here I've just stolen some random images from a three-dimensional virtual museum the other day just to put up some examples, right? Not only these objects are very complex in their geometric shape, even worse, we don't know a priori their size and geometric measures. Numerical analysis has helped a lot in performing simulations on complex objects. So if you're designing a car and the gears in the car, you design the object and the gears forming the engine of the car. But for those, we have very precise technical drawings, and the piece is made after the drawing. So I don't need the piece to know how it is done. I just look at the drawing. Typically, for a work of art, we have, if we are lucky, some sketch made from the artist before actually working on the piece of marble or whatever. But such a drawing is not available. If we are working on a piece of art, we need to get the geometry from the object itself, like a posteriori. Okay. And one of the best possibility to acquire the shape of an object is three-dimensional laser scanning. Three-dimensional laser scanning gives us a set of points, we call it a cloud of points, that belongs to the surface of the object. But that's clearly not enough for us to perform computations on the object. Okay? This is just a random set of points unconnected to each other that belong to the surface. Before we can actually perform a simulation, we have to build a triangulation of the surface, and even worse, we need a discretization of the interior of the object. So we must take the three-dimensional volume of the object and split it into small pieces, be it little squares, little tetrahedra, little whatever. But this process must be done. And what's worse, this kind of, for example, this passage is done. Okay, all the people dealing with the three-dimensional virtual representations of objects of art are already doing this step. But if you build a surface triangulation for visualization purposes, you don't have quality requirements on the triangulations like those that we have for the numerical computations. If you look at this triangulation, you will notice that most of the triangles are close to equilateral. And if the discretizations that we use are close to being regular, then the numerical methods will perform much, much better. Up to the point that if this property is not fulfilled, many methods will actually simply break down. And so even though this first step from the points to the triangulation can be done, most often the triangulations that are obtained are not very regular, or even worse, they're not watertight. Now imagine being a computer and being asked to start from a surface triangulation and fill in the interior with little shapes. If the surface is not watertight, you, as a computer, you don't know what's inside and what's outside. So this second step, if the triangulation is not watertight, simply can't be done. And if the triangulation is bad because it has little elongated triangles and so on, even the interior discretization will be bad and not usable for us. So the idea that we had some years ago was to try to skip entirely this process. We did one numerical methods that do not rely on a mesh of the object, on a conforming mesh, a mesh that actually describes the shape of the object. And so the idea was to resolve this level set techniques, which are a different way to perform numerical simulations. So I'm making pictures in 2 dimensions now because it's is hard to draw in 3D. So that really everything works in 3D as well. So what's a level set method? A level set method has a mesh, but it's just a background mesh. It's just this, for example, this square regular mesh over there. The mesh is not conforming with the object. So the object is this blue stuff here, and you see that the little pieces of the mesh do not match the boundary of the object. It's just a background stuff that is there because I need to store the variables somewhere. The object is really described by what's called a level set function. And the level set function, in principle, could be any function which takes negative values inside of the object and 0 value on the boundary of the object. As a matter of fact, if this level set function is a distance function, then everything works a little bit better. But basically, the idea of level set method is the following. You abandon the request that the mesh matches the object, and you describe the object somehow in this implicit way. You say, okay, I've got this function, and I can store the values of this function phi at the vertices of my mesh, and I define implicitly the object, so the stuff I will be making computation on, implicitly by saying that it's made of this set of points. And by the way, the process of going from a cloud of points to computing this level set function phi is somehow a solved problem. So this is just an example. It's probably not very visible, but I've just stolen a picture from a poster from a conference. This is from a PhD thesis written a few years ago, but there are many places in the literature where it is described how you can therefore move from the cloud of points to the level set representation of the object. So I'm not gonna be concerned on this step here. I just want to tell you a little bit on how we actually perform the numerical simulations. So what we are given is a grid. There's one that is represented here in gray. I've cut away part of it so that we can see inside, of course. And then we are given a function. The values of this function are stored at the vertices of the grid. The domain is that one. So the first thing that we do is that we classify the vertices of the grid into the set of internal points, which are the blue here in the picture. And then we're going to need also an extra layer of points around the object. And these are the red ones in the example. And then what happens? Sorry, there are a couple of slides with formulas. But basically, what happens is that when I discretize some differential operator at some point, if the point is close to the boundary of the object, my approximation formula will involve the values of the variable outside the object. So if I were to consider only the equations for the internal points, I would end up with a system which has less equations than unknowns, because this red variable is appearing in the equation, but I don't have enough equations to determine it. So I need to add something to the system. And this something is actually, of course, the boundary conditions. The boundary conditions are imposed in this way. When we have a ghost point, by using the level set function, it's fairly easy to project the ghost point onto the real boundary of the object, which is dashed here, because remember, the object is not something physical in my code. It's just implicitly defined by the level set function. And then you gather a stencil that is made up of ghost points and internal points, and you formally write for example, an interpolation polynomial on the stencil And by using this interpolation polynomial formally, you can write the constraint that the value at this point hg is some given number, or the normal derivative at this point as some given number, and so on and so forth. And these kind of equations are just added up as constraint to the system to be solved. At this point, we're happy because we have as many equations as unknowns, and we can see. Let's sweep under the carpet all the numerical difficulties to do this. But everything at the end of the day, the hard part, the hardcore part, boils down to solving a linear system whose matrix represents a Laplacian operator in some funny way, because these equations with the constraint make this matrix not symmetric and not positive definite. So it's a little different than the usual Laplacian. It's a little nuisance, but together with Armando has developed in this PhD thesis this geometric multigrid that is optimal for this task. So enough for mathematics. Let's just move to some examples. Unfortunately, the code actually started running last Thursday afternoon, so I don't have real life examples to show. I just chosen some shapes just to perform some prototypical simulations. So recall, inner points in blue, layer of Gauss points around the object represented here in green, but implicitly defined in the method. So the code is based on the PETSI libraries, as we have had no time to perform any optimization, but still we are already scaling reasonably on high performance computing. And I've done some profiling that indicates that most of the time is spent in the linear system solves. And since we are now using stop solvers from the library, we have some hope that putting in our multigrid technique will speed up everything. But it's already reasonable and can perform some computations. So what can you do with this toy? With this toy, you can take an object. Here is just sort of star-shaped, rounded, can't even describe, but you can probably guess from the picture what's the shape of the stuff. And you could compute the evolution. This is the concentration of gas penetrating into the object, time evolution of it. And of course, together with the concentration of the gas, you update the concentration of marble. So you could imagine to perform some measurements afterwards. These numbers are in entirely arbitrary units. I'm sorry, because the model is not being calibrated. But for example, you can reconstruct this is the isosurface where there has been a certain amount of loss of marble, and by measuring the distance from the real surface of the object, you discover not only that when you have a sharp tip, you form more gypsum, but then you can also compare the numerical values. So how much more there than here, and so on and so forth. And so we have still some stuff to do on the code and on the mathematical method, but already in its in the present form, the code is ready to be run. And what we'd love to do is to have some real case, the closest to reality, the better, where we could actually perform a computation, and even better if it's useful to some of you for some real life problem. So that's what we can do right now. What we would like to do in the future is that this kind of method could be extended by changing the level set in time to perform simulations of mathematical models that involve swelling of the material, or by considering more than one level set function, we could do simulations for models that have layers and different equations being active in each layer. But for now, really the take-home message is, if you have a case study, just knock it out of the door. We're ready.
Thank you. Thank you very much. There are some questions, of course.
Thank you, Matteo, for your presentation and very interesting points. I have two questions. The first one is, what is the grid with respect to the count of points that you are using? What's the mesh you have to use? There is a relation with that?
In principle, not. In practice, the coarser the mesh, the more smoothing of the fine feature of the surface you will be doing. So in a practical case, I'll expect the mesh to be fine enough. I expect to need a mesh that is fine enough to describe the features of the object, but not so fine that I will pick the noise in the data, because I do have actually sitting on my computer some laser scans of a ceiling in Turin, and what you can clearly see in that data set is that the data from the laser scan are really, really noisy. So mesh will need to be reasonably fine in order to describe the shape of the object, but hopefully this level set technique will also help in smoothing some of the noise of the laser scan data.
Okay. And another problem which is quite relevant is the scales of this kind of phenomenon. Here, a big problem, that's a problem we have is that the scale of an artifact is much bigger than the region where you have something. Okay, I mean, maybe for civil engineering, some I don't know, concrete and so on, maybe you can see what is happening, but on marble, for instance, or general monuments, even on roads, you can, I mean, the layer you have something is another order of magnitude to respect to the object. So maybe some adaptive mesh would help to improve the, I mean, because computation, you are doing the computation everywhere. So, I mean, some problems will be solved by some clever choice of the mesh near the bound. I don't know.
Yeah, sure. The good answer to your question is really employ adaptive mesh close to the boundary. Another answer, which is quicker to develop and implement if you want to run a computation tomorrow, is that we can throw away from the mesh everything which is further away from the outer shell. By using the level set function, I can know and I can keep inside the computational mesh only those points that are within a given distance from the boundary. And since almost nothing, at least in this kind of phenomenon, is happening further away from the boundary, applying homogeneous knowing on the close to the mesh that was thrown away, would already be a way to perform the computation on a much smaller set of points and obtain something that is close enough to what we would obtain with AMR. But surely AMR is the way forward.
Okay, are there other questions? There is one online and one here. So we have time, I think.
It's a curiosity because we start with a very complex object, a head or something. So it's not only a question for you, but also for other people. So it seems because from Matteo Semplice you have a lot. I think it's not possible to model a head or something very big with a simple one level set. So my question is possible to, or is interesting only to consider a small region of some artworks, or you need in some simulation to model the whole piece? What is, I don't know if the question is clear, because
yeah, the question is clear, but it's not a question for me.
yeah.
I can actually do what you suggested. But what I will actually do is what I'm asked to do by the person who's giving me the actual real life problem. Yes, of course, we can perform a simulation on a smaller bit.
Yes, you use as a your thing as a basic as a basic element, and then it's possible to reproduce in different way.
Yes, sure, we can perform a computation on the nose, on the finger, on a small piece. Yeah, sure.
Okay, another question from the audience online.
Yes. Very nice talk, Matteo. I really liked it. I have.
We cannot hear you, but just a second.
Can you hear me?
Try again?
Okay, can you hear me?
Yeah. Sure.
Okay, so very nice talk. I really loved it. I have one comment on the very first part that you of your talk concerning to the problems with TET meshing. What I want to say is that actually there are quite, let me say, mature methods for meshing, producing also watertight and two manifold, or let's say manifold meshes also in 3D nowadays. And my question is actually related to the use of the grid mesh that you need to activate the level set. In part, Roberto already asked this. It's not, is it correct to say that the regularity of the grid is not a constraint? So you could also have cells with varying dimensions around the object. Is that correct?
Yes, sure.
And
what Roberto was suggesting with the adaptive mesh refinement idea.
And do you think that to have regularity, so structured grids is also a need, or you could also think about discretizing the domain around the object with other cell types?
With other, sorry?
Grid or cell types, to have cells that actually are not regular, because the key ingredient for you is to be able to project on the boundary, on the real boundary.
Yeah. Typically, when one does this level set computation, the grid is in fact some background object that is just used to store the values and to locate values in space. And therefore, typically people choose very simple grids because they are easier to handle from a computational point of view. So that's why people typically use regular Cartesian meshes. And it is possible to move to adaptive meshes, and the choice typically goes into octree type meshes. So still made of cubes, but not all of the same size. But yes, in principle, you could do you could implement a level set method on any kind of background mesh, which is I just don't see the need for it.
Yeah.
Maybe you have a good taste.
Yeah, and probably at the end, if the grid is too much adaptive, then it's better to switch to a polygonal or polyhedral. So
Yes, I mean, we could have a good mesh, then just use finite elements. Sure. Then the only fact is that all the people I talked about, they told me that their finite elements broke down because of the grids they had. So that's why we have been investigating these other approaches.
thank you.
Thank you. There was another question. No? Okay. So thank you again. Okay. Third speaker of the morning is Maurizio Ceseri from CNR in Rome, who will talk about a mathematical model for concrete carbonation processes. So, please.
So, good morning, everybody. Thanks for giving me the opportunity to talk about this project. This project is a joint work with, oh, sorry. This project is a joint work with Gabriella Bretti and Roberto Panini of the CNR, and with Maria Carla Ciacchella, that has already discussed some similar problem yesterday, Maria Laura Santarelli, and Giulia Gapparendo of the Department of Chemical Engineering, Materials and Environments at the Sapienza University in Rome. Now, we talk about carbonation of concrete. The same topic has been discussed on Monday morning by Francesco Freddi. I'm here just to resume some of the feature of the process. Concrete is formed by a piece of calcium hydroxide. Sometimes there are present some steel bars to give much more strength to the piece of concrete. The environment of the concrete is alkaline, so this forms a thin protective layer around the steel bars that prevents bars from corrosion. Now, if the piece of concrete that is in contact with the ambient air, in particular with the carbon dioxide also and also some moisture from the outside penetrates the piece of concrete. Now, within carbon dioxide reacts with calcium hydroxide and forms calcium carbonate. So we have two different regions, a carbonated regions with calcium carbonate and an amplified region with calcium hydroxide, which is that are separated by a carbonation front, which in general might not be a sharp interface, but a fringe region. Moreover, the carbonated region is very acidic. This destroys the protective film around the steel bars. And this, as already discussed by Francesco Freddi, causes cracks in the carbonated side. The overall reaction, chemical reaction, is given by this. So calcium hydroxide reacts with carbon dioxide to give calcium carbonate plus a molecule of water. However, this reaction is the result of intermediate reaction steps. Which are these steps? First of all, we have the water, a molecule of water reacts with a molecule of carbon dioxide to produce carbonic acid. This is the first reaction. The second reaction is the carbonic acid realizes two subsequent dissolution and forming a molecule of carbonate plus two ions of hydrogen. The third chemical reaction is those products, the product of the second reaction reacts with calcium hydroxide and forms calcium carbonate plus two molecules of water. This is the whole process of carbonation. As it is already known, this reduces the pH of the environment, making the environment more acidic. And also it reduces porosity of the carbonated region with respect to the upper part. However, according to the chemical engineers, this is not finished. In fact, there is another reaction involved. This reaction says that the calcium carbonate already formed by carbonation dissociated itself in an ion of calcium plus an ion of carbon. This fourth reaction has not been very studied in the research, and we are going to introduce in our model. This, in particular, this reaction is a slower process, very slow with respect to the other three reactions, and also it increases porosity, contrary to the whole process of carbonation. So we are going to develop a model concerning all these reactions. Now, the model has been developed following work of Aline, Natalie, and August. This one that has already cited by Mario previously. These are the six components of the model. So we have the transport of water inside the concrete, carbon dioxide and carbon that reacts together, calcium hydroxide, calcium carbonate, of course, and finally calcium ion as the final product of the dissociation of calcium carbonate. So, first of all, let us describe the chemical reactions involved. First of all, the reaction between carbon dioxide and water to give carbonate plus two ions of hydrogen. In principle, this should be a second order reaction, so involving the product of carbon dioxide plus water. However, in this case, the concentration of water is much higher than that of carbon dioxide, and so in this case we can approximate the whole reaction by a first order reaction, just considering the concentration of carbon dioxide. The second reaction, so calcium hydroxide reacting with carbonate and ions to form calcium carbonate, is a second order reaction involving the product of carbonate and calcium hydroxide. The last one is the dissociation of calcium carbonate. And this is, again, the first order reaction involving only the concentration of carbon. Now, let us consider the equation for water. This is given by a transport and reaction equation. The transport term is given by, of course, the Darcy's law that is written here in diffusive forms. The diffusivity term here, it depends, of course, on the water content plus porosity and the porosity of side. As we found in literature, we define this. We consider this formula for the diffusion. So we essentially separate the contribution of epsilon with the contribution with the water. The exponent 19/6 is a fitting parameter to take into account.
The rest of the script.
So also that. It is easier to remember when you do some calculations. Of course, W min is the residual water content. Concerning D star, the contribution of water content is given simply by an exponential form with A and B some fitting parameters. Concerning the reaction term, the reaction term is simply water is produced by the reaction between calcium hydroxide and carbonate, and it is consumed by reaction with carbon dioxide. Now, let us consider carbon dioxide and carbonate. These both are transported and diffused in water. Concerning the reaction term, carbon dioxide is only consumed by reaction with water. Concerning carbonate, it is a similar equation, so we have transport and diffusion, and but the reaction term is a bit more complicated. It involves all the three reactions. In fact, in particular, carbonate is produced by the reaction of water and carbon dioxide, and by dissolution of carbonate, and it is consumed by the reaction by reacting with calcium hydroxide. Now, the last three equations are more simple because we assume that they are not transported nor diffused in water and are only given by reactions. So we have three ODEs. Of course, they vary in space because of their dependence on carbonate and also carbon dioxide. And in particular, we have calcium hydroxide is consumed only by reaction with carbonate, calcium ion is consumed only by produced only by dissociation of calcium carbonate, and calcium carbonate is produced by this reaction, and it is consumed by dissociation. Okay, but in fact, this system of equations can be simplified. In fact, we can see that a linear combination of these three equations makes it possible to express the calcium carbonate as a function of calcium hydroxide and calcium ion. Now let us see the equation for porosity. As in the words of Ali and Natalini, we can evaluate the porosity in this as this equation. In particular, these three constant, epsilon 0, 1, and 2, is epsilon 0, the initial porosity. Epsilon 1 is the porosity when calcium hydroxide is completely consumed, so when in the completely carbonated region. Epsilon 2, it takes into account the variation of porosity when calcium carbonate is soluble. And this is the whole mathematical model. So concerning in this first in one-dimensional form, we have three transport diffusion and reaction equations. Two ODEs takes into account only reaction terms, and two algebraic equations for calcium carbonate and porosity. Now, the boundary conditions. If we assume that Z equals 0 is the surface exposed to the environment, we assume that, of course, on the other boundary, there is no flux outside, from outside, and we impose additional conditions on on water content as a function of the relative humidity and the temperature of the ambient. Concerning carbon dioxide and carbonate, we assume that a flux condition depending on the difference between the calcium dioxide on the surface Z equals 0 and the ambient concentration of calcium of carbon dioxide. Ka and Kb are constant that will be determined by calibration. Now, we made some preliminary simulations and we try to compare our solution with some experimental data from this paper. Now, we consider for the moment only accelerated conditions. In many experimental data sets, since the carbonation process is quite slow, we consider accelerated conditions. So essentially, we increase the concentration of the ambient air, of the ambient controlled environment of the carbon dioxide up to, for example, 20%. Just to have a comparison number, the natural condition of the natural concentration in the environment of carbon dioxide is around 0.03%. And also we consider here relative humidity of 80% and temperature of 20 degrees. Now, this is the calcium carbonate after 14 days. The blue line are the experimental data. The red line is our simulation. We can see that the simulation capture the main behavior, but in this case it underestimate the degree of carbonation in this part. Concerning carbon dioxide, again, the black line is the experimental data. The green line is the simulation. Here, again, we have this. We capture the shape of the same S shape of the results of the experimental data, but we underestimate here and we overestimate here we overestimate the carbonation here, we underestimate carbonation here, but we capture essentially the region of the carbonation here. Now, we just made some simulation on a simplified model concerning only the reaction terms. So we neglect, in this case, transfer and diffusion, and we focus only on this ODE's system. First of all, just discuss about the time scales. Essentially, the three reactions have three different time scales. The fastest one is this reaction, the reaction producing calcium carbonate. The slower, as we have already said, is the dissolution of calcium carbonate of several orders of time. And in fact, we can see that if we consider only the evolution of carbon and calcium carbonate, we can see that both increases very quickly, and calcium carbonate decreases very slow, and carbonate increases again very slow. If we make a zoom, we zoom on the first instant of simulation, we can see what happens. First of all, calcium hydroxide in a few seconds, after a few seconds, almost disappears. And at the same time, calcium carbonate, calcium carbonate increases and reaches its maximum. Then it starts decreasing, but we cannot see here the decrease because of the lens. Concerning carbonate, it decreases because it is consumed by carbonation, and then it starts increasing. This increasing is determined by the consumption of carbon dioxide. Once the carbon dioxide is consumed, then carbonate keep increasing, but at the pace of the dissolution of calcium carbonate. Now, just have a look on porosity. Again, we can see the same dynamic. It decreases very fast at the beginning, and then it increases very slowly. And this is assumed in the first instant of the simulation. So, what are the future perspectives of this work? First of all, to perform detailed calibration of the models for several data sets, and hopefully also experimental data produced by our colleagues, and also to evaluate the evolution of porosity and see if we can capture this behavior, and also try to simulate both accelerated and natural conditions to evaluate both conditions. So that's it for me. Thank you for your attention.
Thank you. The leg is there. So, are there any questions, comments? Please.
Please sit down.
Especially first time.
No,
Yeah.
it's a Zoom thing, so hi Maurizio, thanks for the talk. I have maybe a lot of things to talk about, but it seems that you say that there is an accumulation of carbon ions in concrete or in this type of materials over the time, which is usually not taken into account by standard carbonation. I think you're right. But then I have a modeling question. Since you have ions of one type, most likely in the material there are other ions as well. Doesn't make sense to take into account the transport charges, because they will change the transport equation. You have some, you know what I mean? It complicates further the whole,
Yeah.
but on the other hand, you have lots of time scales. Sometimes, okay, you may disregard some time.
Yeah.
That was my point.
No, that's probably something to take into account in a future evolution of the model. At the beginning, we just keep the model simple, just because it's quite complicated in this context. So once we are sure of the dynamics, also we can see one of the biggest problems is that on this part there is no such a big literature. So we don't have too much data to evaluate all this. But in fact, this is something to take into account. It is quite obvious to keep calcium carbonate and calcium hydroxide fixed, so that's not they are not transported, not used in the system. But maybe it makes sense. It might make sense to consider the transport or diffusion of the calcium ion. Doesn't make sense.
Carbonate.
Calcium ion. Calcium.
Any other questions, remarks? I have a question. Your model seems to capture very well the overall behavior of the reaction. But do you have any idea of why the beginning of the reaction and the end of the reaction are underestimated and underestimated? Where does the difference between the data and the model?
Yeah, we have to work on it. We have to adjust some details. In principle, we should do a calibration.
Okay.
These are here. We just do some tuning of the parameters just to see what happens and what is
The behavior, the general. Any other?
The match is perfect and something goes wrong.
You just interpolated it.
Yeah. Yeah, we make errors, they are making errors, so we need to.
So, thank you again. And